Okay, so for this class, I want to start with a review and an ending of how to optimize functions when there's only one choice variable. One more example of that, and then we'll consider that section done. The next section is going to be a look at matrices and how to work with matrices. That it's kind of just a good skill to have in general. Anytime you see something math related in the future, if you have an idea of how matrices work, it might give you some insight on how whatever it is you're seeing can be interpreted a little bit better. You might say, what do matrices have to do with like an equation, y equals f of x? That's not a matrix. Okay, you're right. But if you have multiple equations, multiple functions, maybe there's some way to think of them as all part of one big matrix. And that's what I would like you guys to have some familiarity with. I'm not sure we'll get through that all today. Another point for the class is that I do want to have our second quiz on Thursday. The syllabus says February 18th for the second quiz. So I want to go ahead and do that. And it's going to mostly be over this optimization problems when there's only one choice variable. Pretty much expect that type of a problem on the quiz on Thursday. I might throw in something about matrices depending on how far we get today. Just a simple question about matrix algebra, but I'll let you know whether that will also be on the quiz. Either way, quiz Thursday. Okay, let's start with this example of, it's from the Sid Sayer textbook, which I left in my office. I don't have it here to show you, but hopefully some of you know what I'm talking about. It is, where is it? I don't see it. Gone. Oh, here it is. I just had to click on the button. It was downloaded, but it wasn't opened. Pardon me. Now I should be able to share with you. Or can I? Share screen. Where is it? This is weird. It's clearly there. There it is. Took a while for it to be available for me to share with you. Pardon my technical mistakes. Okay, so we were talking about this last class, chapter 8. And the thing I want to do now is the very last example, which is a Dutch flood problem. And let's think actually what these Dutch people were thinking in 1956. This is a really old problem, 1956. Here's the government of the Netherlands who decided they have to build a whole system of dikes to protect the country from floods. There were too many floods. The cost of the flood damage was too high, and they figured, we've had enough of this. Let's just make a big investment to stop the floods from happening. And so what they did was estimated not the cost of building the dike, but the cost of flood damage and the cost of the dike together. Okay, so I0, let me explain to you what this in this fixed, it's called an objective function. The thing that they want to minimize is what's in braces here. I0 is the fixed cost of the dike. It means that the stuff you have to spend no matter how tall you make it. K is the marginal cost of building the dike up higher. So the higher, X is the height of the dike. So the higher you build X, K is the sort of fixed marginal cost. That's how that part of the cost is the marginal fixed plus the marginal cost of the dike itself. And then the second thing, I'm sorry, it's the third. The third term here is the cost of the flood damage also. And as you can see, it has this sort of exponential aspect to it where X is a negative alpha X in the exponent. What does that mean? That means the larger X gets, the smaller this damage gets in probability and everything. So this is a non-trivial problem. The question is, how tall should we build the dike? And the answer is, well, we want to minimize this objective function where my choice variable is x and my choice set, remember that's the set of all possible x's I could choose. It's just any number greater than or equal to 0. Okay, so there's a corner solution at, I'm sorry, there's a corner point at 0, but there's no corner to the right. This is maybe the first problem that you've seen where it's like there's one corner, but not two. And that's okay, you could just check the one corner. Let's go on. Oops, what am I doing? Here we go. And maybe this matters. This coefficient a for e to the negative alpha x is actually also very heavily parameterized. P0 is the probability dikes are flooded. V is the cost of flood damage. Delta is the interest rate. So all of this goes into this coefficient a. Here's the problem. Solve for x. Okay, you can do that. And another thing, consider how the optimal x star depends on P0, V, delta, or K. In other words, find the sign of the relevant comparative static. I don't think I've given you many problems where I ask you, I did on actually quiz 1. If it was a bonus for quiz 1 or something, or a bonus for homework 1, I asked you to do some comparative statics. But here I'm asking you again. You should not think of P, V, delta, and K as variables. Don't think of them as variables because they're not. Think of them as something which is fixed in the problem, but it could change if we considered a whole class of problems. And so the technique is first solve for x star. X star is the thing that maximizes this problem, and then see how that x star depends on P, V, delta. Okay, in other words, take the derivative of x star with respect to P0, V, delta, and K. That's what comparative statics means. Okay, you guys want to help me do this? I will share my, what will I do? Share a different screen or? Kx plus alpha ae to the negative alpha x. I want to share, or not share, pinpoint, spotlight for everyone. Okay, here's the problem. What do I want to do? I want to find the x which minimizes this function. You guys tell me what is the first thing I should do here?
The derivative.
Take the derivative of the objective function, right, Kai?
Yeah.
Very good. With respect to x. So I0 with respect to x just disappears. There's no x in it. Kx becomes k. I'm going to call this the first order condition, if you don't mind. First order condition, colon. That's like my way of writing first order condition. What follows is going to be the first order condition. It should be that k, that's the derivative of this part. Now we have to take the derivative of this. What do you get? There's going to be a minus out front. I'll give you that part. Can you see it on the screen? It says a e negative alpha x. Let's see, what's the derivative of that with respect to x? Anybody got an answer?
A e to the negative alpha x times negative alpha.
Very good. And I'm gonna put that initial alpha that you said at the end up here at front. Negative alpha a e to the negative alpha x. That's correct. It's kind of key that you treat all those other letters as they're fixed, because in this problem where the only choice variable is x, you can tell the choice variable is x because it's written right underneath the word min. So that's the only thing that varies. All of those other things should be treated as constants, which you did. I'm not sure who answered that. Who was that? Who said that? Whoever said it was right. And the first order condition is that you set that equal to 0. Correct? What's the problem say? It says solve for x. This isn't solved for x, but maybe you can see how pretty easily it can be solved for x. What should we do? Maybe move this to the other side. Let's divide by alpha and A. Now you guys have any ideas what to do? I'm trying to solve for X. What should I do?
Take the natural log of both sides.
Who's talking? I can't tell. Who said that? When I have this video spotlighted, it doesn't tell me. You were correct. Whoever said that, I just want to give you credit for it. No one wants to take credit for saying that. This is weird. Does anybody know who it was? I'm gonna ask you to call out this person. I apparently can't tell who it is. Well, whoever mystery voice was correct. Let's take the natural log of both sides. The natural log of E of something is just the something. Those are inverse operations, and so they cancel each other out. Natural log of E to the negative AX is just negative AX. Now let's divide both sides by, I said A, I meant alpha. Negative 1 over alpha times natural log K. And I'm going to put a little star there, indicate that we're done. Now, you guys see how I got that? You think you'd be able to do that on a quiz? Solve a maximization or minimization problem? Oh, should I look at the second order conditions? What do you guys think? Real quick, let's just do it. Second order conditions. For a minimization problem is what? I want to take, this was the first derivative. So I want to take the derivative of that with respect to X. What will I get? There's another negative alpha that comes out. It's got alpha squared A e to the negative AX. This is positive. This is positive. This is, how do I know A is positive? I guess you should go check and see what A is actually. And that is, let me write A down for us to have. A equals P0, the 1 plus 100 over delta. Okay. That's always positive. P0 is always positive. V is always positive. 1 plus 100 over delta is always positive. E to any power is always positive. So the second order condition is that this is greater than 0. It's met, right? Because a positive thing is always greater than 0. 3 positive things multiplied together, always greater than 0. So we're good. This is indeed a minimum. Remember, it's kind of flipped, not really flipped, but maximum means the second derivative is negative. Minimum means the second derivative is positive. You guys agree? You guys following? So we are not done. Let us think about these comparative statics, because I think it's a good exercise now to say this isn't it. We're not done with the problem. We've learned something about X star, but and in fact, this would be useful if you're the Dutch government. If you're the Dutch government, you want to know how tall to build your dike system, that's your answer, X star. But if you want to know something more, which is how does this depend on P, V, delta, and alpha, I think those were the 3 I asked you to look at. That's when it's a comparative static question. And I want to take the derivative, not of this original function. Don't take the derivative of this original function with respect to those parameters. Take the derivative of the X star with respect to those parameters. So let me rewrite for you what X star is. Maybe put them both on this thing here. But now instead of A, I'm going to plug in what A actually is. And that is X star equals negative 1 over alpha times the natural log of k over alpha times a. Now instead of a, I'm going to put in all of this junk. 0 v 1 plus 100 over delta. Okay. Oops, I went off screen a little bit, but there's x star. That's the x star we found, unless I made a mistake. That's the right x star. So if I ask you guys to find a comparative static, what I'm asking you to do is first solve it, then take your solution and take the derivative with respect to whatever I'm asking you to take the comparative static with respect to. So for, let's say, alpha, I need to take the derivative of this with respect to alpha. That's hard. I don't know if I even want to do that. I think you're going to have to use the product rule just to do that. To take dx star d alpha, I don't see any way around using product rule. Doesn't seem like fun. Maybe I can do it. Anyway, I won't make you guys do it. I'll do it. Tell me if I got anything wrong when I do this. Okay, product rule. First, I'm going to take the derivative of this. So that's derivative of the first thing times a copy of the second. Now it's the copy of the first thing times the derivative of the second. The derivative of natural log of something is 1 over that thing. In other words, the reciprocal of what's inside these parentheses. I'm gonna write that. Alpha P0V 1 plus 100 over delta over K. See what I've done there is just I've flipped the numerator and the denominator of that fraction, because 1 over a fraction is just to flip the fraction. I'm not done though, because I have to multiply that by the derivative of that with respect to alpha, which actually isn't that difficult. It is simply a copy of that without the alpha. So this, I don't have room for it, but this times pardon. Now I need to flip the fraction again, right? Because I actually want the derivative of this thing before I took the derivative. The derivative of what's inside the natural log with respect to alpha. Okay. I hope this isn't too confusing. I want to make sure we get this step too, which is that right now I'm taking the derivative of this thing here, natural log of the junk, and it's going to be 1 over the junk times the derivative of the junk with respect to alpha. That's why I'm going to look at this and put this fraction there, k, p0, v, all that stuff. Everything except, oh my gosh, wait a second. Alpha's in the denominator here, isn't it? Not the numerator. Okay, I can still do this. Alpha's in the denominator. So k p0 v 1 plus 100 over delta. Now I want to take the derivative of 1 over alpha, which is actually negative 1 over alpha squared. Okay, so it's this x is actually not an x, it's a multiplication symbol. So this, it would go there if I had room. Right? So here's how you read this. Dx star d alpha equals 1 over alpha squared times the natural log of k over alpha p0v times 1 plus 100 over delta minus 1 over alpha times alpha p0v times 1 plus 100 over delta over k times negative k over p0v 1 plus 1 over delta over alpha squared. Really long way to get at what we want here.
How'd you get the delta squared at the end?
Oh, did I say delta squared? I meant alpha squared.
Oh, okay, no.
That should be an alpha.
Okay, yeah, I see that.
So can I just say, I've written this, I've done this in a way that I myself wouldn't normally do it. And that's because I just wanted to show you how to take the derivative of something in a very algorithmic step-by-step way where you're not even thinking about ways of simplifying it before you take the derivative. In reality, we should have simplified this before we take the derivative, because natural log has this nice property where you can break it apart. Natural log of things that are multiplied together can be very easily broken apart into separate natural logs. And had I done that, all of this algebra here and all these fractions wouldn't have even been part of our problem. However, I didn't do it that way. I just wanted to show you a sort of direct application of the product rule. Here's what you would get. You guys think I made any mistakes? You think this is right? What do you think? Let's simplify it. And then maybe, if we have time, compare it to the other way, which would be to use the properties of natural logs to simplify it before we took the derivative. And if we get the same answer both ways, that's pretty good confirmation that it's correct. But before I do that, does anybody have any questions over just like how I got to where I am here? Remember, this is the product rule, so I'm taking, it's like U times V becomes U prime V plus V prime U. That's what I'm doing. Okay, no questions? I'm counting on you to ask the questions if you have them. Okay, let's simplify this because it looks ugly. I didn't change much of that. I didn't change anything in that first term. I'm hoping I can simplify a lot from the second term here. And that is the K's cancel, the K's cancel, the P's cancel, the V's cancel, that cancels. Only thing we have left is so I have an alpha in the numerator here. Is that right? I think it is. And I have an alpha squared in the denominator, but I also have a negative alpha out here. So what do we get? Here's how I'm looking at it. I see 3 alphas in the denominator and 1 alpha in the numerator. I'm going to call that 2 alphas in the denominator, or 1 over alpha squared. Now I'm going to think about it, is it minus or plus? There's a minus here, there's a minus here. It's actually a plus. So this whole stuff just goes to plus 1 over alpha squared. That's what I get. You guys agree with that? Let's leave that for now. And now look at what would happen if I had used my simplification before doing all this. And really, I want to rewrite this up here as something else using my natural log properties. You guys know what I mean by those properties of natural log? This thing here can be rewritten as the natural log of K minus the natural log of alpha minus the natural log of P0 minus the natural log of V minus the natural log of 1 plus 100 over delta. I know you can't see all that stuff very well, but by rewrite here, let me rewrite the whole x star equals -1 over alpha times this. And what I've done is don't even worry about all these other things because they're going to just disappear when we take the derivative with respect to alpha. It's really just a way to separate out this fraction inside the natural log as one positive term because it was in the numerator, and then the rest are negative terms because they're in the denominator. That's a real simple, it's a real neat trick, I think, for simplifying natural logs. Now, if I want to take the derivative of just what's in here and just what's in the parentheses, I'm sorry, I just ran out of space to really write that clearly, but I want to show you now that it sort of doesn't matter because I have to write it above, right? What is the derivative of what I have in the parentheses with respect to alpha? Let's do it term by term. The natural log of k, 0. Natural log of alpha is, okay, 1 over alpha minus 1 over alpha. Everything else, 0, 0, 0. See how it all just went away? Wasn't that a lot easier than not simplifying the natural log? Okay, so this tells us that the derivative of everything inside this parentheses with respect to alpha is just -1 over alpha. That's exactly what we got, because when you take this -1 over alpha and multiply it by the -1 over alpha there, you get 1 over alpha squared. So thinking about it the other way, we get the same answer. That makes me think it's probably right. Okay. And you may be thinking, well, how am I supposed to do it? Which way should I use? Should I simplify it before I take the derivative or not? My answer is it's up to you. You can choose to do it that way if you'd like, or not. The best thing to do is get some insight over whether or not it'll help you to simplify it and do whatever's easiest. If it will help you to simplify it considerably, save yourself some time. Also save yourself the possibility of making mistakes. A lot of times we make a mistake because the more algebra we give ourselves to do, like copying from one line to the next and then canceling out and copying and everything we do, that's the more possibility for mistakes. So if by simplifying, you've made it less copying and less algebra, then it's probably a good idea because it reduces the probability of a mistake. But I will definitely leave that up to you. I'm going to look at the original problem to see if it says anything regarding the signs of this stuff. I don't think it does it? That's okay. I'll just consider how the optimal x depends on, find the sign of the relevant comparative static. So how do I find the sign of that? Oh, I didn't ask you to do it. Dang it. Sorry about that, guys. I didn't ask you to do the alpha because I guess it was so complicated, but I have no regrets because I wanted to show you, I'm glad I showed you something that was computationally difficult. Computationally, algebraically, just writing out all those lines was difficult. It's actually not really clear to me whether this whole thing is positive or negative. That's okay. That's okay. What's more important to me is that if I asked you to find this dx star d alpha, you would be able to. This is something I would be more likely to ask you in a homework rather than in a quiz, because just wouldn't. I fear it would take too long for you to do it in a quiz. And I'm not really asking you to spend 20 minutes on algebra during a quiz. I'd rather you demonstrate your knowledge of the procedure of optimization rather than the technical details of the algebra. Okay, so if I do give you something on quiz 2 about optimization, and I will, and there are some parameters in it, like alpha, P0, V, delta. You should understand the process of what I just did in order to A, solve the problem, and B, determine the comparative static calculation of that problem. But maybe this will ease your mind a little bit. I'm not going to make it this intense of all the algebra, okay? Because that would take you too long, and I don't want you to spend too long on that one problem of the quiz, okay? You guys have any questions? I think we should be done with this. I think we should be done with optimization of one choice variable problems. And the next thing I have on the syllabus, it says systems of linear equations. But the more I'm thinking about that, I have to do matrices first. If I jump right into systems of linear equations, which actually you already could solve, you could solve a system of equation if I asked you to do it. That's fine. It's more like I want you to be able to think of it in this other way, and to do that, I have to go over some matrix stuff. So let's do some matrix stuff. Some of you guys have already used matrices, right? And maybe even some of your classes already use matrices. What do you think? Am I right about that? Do I need to stop the spotlight before you can see? How about there? Is that better? Now you can see the PowerPoint slides, right? Okay. Let me just define for you what a matrix is, after all. You probably know, but if you don't, let me just define for it. It's a rectangular array of values. Array means not just one value, but a bunch of values organized in a rectangle. In fact, it's organized into rows and columns, and we call that the dimension of a matrix, m by n. This looks like times, but the word is used as by. M by n matrix. M is the number of rows, n is columns. So that kind of matters. It's row first, then column. If you see an m by n matrix, that means it has m rows, n columns, and not the other way around. If these two numbers are the same, m by n, we call that a square matrix. All right. Stop me if you have any questions. How do we add and subtract matrices? Well, actually, unlike numbers, which you can always add numbers or subtract numbers, matrices may or may not, it might not even be possible to add or subtract a matrix. In fact, it is only defined if the two matrices have exactly the same dimension. Okay, so one matrix can be added to another matrix only if they have exactly the same dimension, okay? If you try to do it with two matrices that are different dimensions, your calculator should say error, or you should say error, because there is an error. You can't do it. How do you do it? You just add things term by term. You just add whatever's in the top left of the two matrices, you add that together, and that becomes what's in the top left of the new matrix. So let's do an example of that. I'm gonna stop share. Let's just show you some matrix. Once again, I think I need to. There we go. Here is an example of a matrix that I'm going to do a 2x2 matrix plus another 2x2 matrix. What do I get? My answer is going to have the same dimension as the two matrices I'm adding together. What do you guys think? What goes here in the top left? It's going to be a 2x2 matrix, top left, top right, bottom left, bottom right. What goes in the top left?
-2.
Yeah, -2. And you just get that by, ignoring all the other numbers. We're just looking at what's here, adding them together. That's what goes there. This is how matrix addition is defined. So I'm not even going to have you guys do the other ones. I think you got it. One. What you can do is check me that I got it right. Let me know if I didn't. Okay. What if it was subtraction? If it was subtraction, same thing. I just take this minus that. I'm not even going to bother teaching you that because I think you know it well enough. But let me know. Oh no, somebody came. Somebody came this late. Let me now talk about matrix. I want to get to matrix multiplication because that one's not as easy. So before I do, let me define for you these other terms. But fine, I'll go switch back to my PowerPoint, or maybe you can't see it, but it says that there's something called an identity matrix, and the property of an identity matrix is that there are ones in every entry along the diagonal, and there are zeros everywhere else. So a 3x3 identity matrix looks like 1 0 0 0 1 0 0 0 1. That's called an identity matrix, and you'll see why that's important later. If in fact the matrix is all zeros, you just call that a null matrix or zeros. Okay, so we have those terms. Let's talk about matrix multiplication now. I want you to be able to see this current slide. Oops, matrix multiplication. Two matrices can be multiplied together only if the number of columns of the first matrix equals the number of rows of the second. So this is not the same as addition or subtraction, where the dimensions had to be exactly the same. It's no longer the case. For multiplication, you don't have to have the same dimension, but this property has to be true, that the number of columns of the first matrix being multiplied has to equal the number of rows of the second matrix being multiplied. Okay, that's important. I'll give you some examples later. The new matrix, in other words, the product matrix, is formed the following way. The new element in row 1, column 1, is equal to the sum of the term-by-term multiplication of the first row of the first matrix being multiplied by the first column of the second matrix being multiplied. Okay, that's a lot of words. It's true, but I'll give you some examples that will make sense of that. So that's just row 1, column 1. But you can do this for all rows and all columns. Row I, column J, where I and J are any number of any possible row or any possible column, is equal to the sum of the term-by-term product of the ith row of the first matrix with the jth column of the second matrix. The best way to learn this is by example. So let's do some examples of matrix multiplication right now. I don't know, that probably, maybe you come back to that definition if you're like, by the end of today, you're still like, I don't get matrix multiplication. Look at a book, look at that definition, and look at these examples I'm about to do right now. Wait. Got it. All right, so what if I wanted to take, I'll take these same two matrices and now multiply them together instead of add them together. I want to see what I get. Not times. Okay, so now I'm taking the same two matrices and I want to multiply them together. Here is how you do it. Let's first, I'm going to go real slow here. The first column, first row is the term by term product of the, let's call this one A, this one B. So right now I'm going to call that first matrix A and I'm multiplying it by that second matrix B. This will just help because I'm naming it. So the first row, first column of AB, that's the product, right? AB. I'm going to say A times B equals AB. we leave off the multiplication and we talk about matrices being multiplied together. You don't have to say A times B. You can just really say AB, and that means A times B. Okay, so the first row, first column, I don't know why I said column first. First column, first row of AB, what is it going to be equal to? It's going to be equal to the term by term product of the first row of A, right, times the first column of B. I want to look back on what I wrote and make sure that it will be clear. Here's what I wrote. The sum of the term by term multiplication of the first row of the first matrix multiplied by the first column of the second. Okay, so let's use that to do this. The first row of A times first column of B. What does that mean? First row of A, first column of B? Well, the first row of A is 2 and 3. The first column of B is -4 and 0. If I multiply these together term by term, that means I'm taking the first two terms, multiplying them, and the second two terms and multiplying them, and then add those together. That's the answer. So what would it be? I need to take 2 times -4, and I'll get -8. Now I'm not done. I also have to take 3 times 0, get 0. The answer is -8. So that is what goes in the first column, first row of AB, is -8. Okay. This is a little, this is a little deceptive, because it looks like I just took the first, it looks like I did 2 times -4 and got -8 and I stopped there. That's not what happened. That's just coincidence, that the 2 and the -4, don't always think that it's just the two terms multiplied to get here. Like 3 times 3, put a 9 here. If you put a 9 here, you might not be right. You still have to use this method. So let's go ahead and do the rest. Let's do the rest of these, if that's okay. What goes in the, let's say the first row, but the second column, okay? The first row and the second column means I want to take the first row of A times the second column of B, 3 and 8, all right? You can see already that it's not going to be 9. It's going to be bigger than 9. It's going to be 2 times 3, which is 6, plus 3 times 8, which is 24. Should be 30. Okay, so our original problem of A times B, we know that the first term here is -8. First row, second column, the term isn't 9, which we would get by 3 times 3. That would be wrong. The answer is actually 30. 30 goes there, okay? How did I get 30? I took this 2 times this 3 and got 6. I took this 3 times this 8 and got 24. Added those together, I got 30. That's what belongs in the upper right of this matrix. How about the bottom left? I'm going to take this row and multiply it by this column. I would get which is -4 plus 0, -4. I get -4 there. Once again, it's not what you would think if you were being naive and just said 1 times 0, you might have put a 0 there. You'd be wrong. It's -4. Sometimes when I'm doing these, like say on a whiteboard, I move my arms in this way. So my left arm I move side to side, and my right arm I move up and down, and that gives you this motion of multiplication, right? or this. I don't know. I don't know if that helps. It probably doesn't help you because you'll just be writing these on paper. You're not going to be doing it on a whiteboard. Okay, but what I most want is for you to understand how this process works. So matrix multiplication, what goes here? Can anyone tell me what goes there? The bottom right of the matrix AB.
3.
That was Jonathan, wasn't it? You can't hide from me. I was looking this time. Jonathan says 3. 3 times 0, he's right? You see how we got 3? 3 times 1 plus 0 times 8 is 3. And that's how matrix multiplication works. So I happen to give you 2 square matrices and asked you to, and together we found the product. They don't have to be square. They could be any dimension. A and B multiplied together could be any dimension as long as not the row, but the column of A equals the column of, the row of B. So let me write that out. This is a 2 by 2 matrix. This is a 2 by 2 matrix. A is a 2 by 2 matrix. B is a 2 by 2 matrix. And AB is going to be a 2 by 2 matrix. Here's a really cool trick that you can always use to learn the dimensions of a matrix multiplication. First of all, see, is it possible to multiply? And if you do, what will be the dimensions of the product matrix? You can take these inner 2 things. So the dimension, this dimension from the first, this dimension from the second, make sure that they're the same and then cancel them out. And then the 2 on the edges will be what remains, 2 by 2. That's what AB is. Isn't that cool? Here, let me demonstrate that. That's worthy of further demonstration, and I will do so now. So if A, can you guys see this? If A is a matrix with dimension 3 by 4, B is a matrix with dimension 4 by 2, what is the dimension of AB? Remember, AB means A times B. And I just told you this trick.
3 by 2.
Great. You guys see how we got that? 3 by 2. The 4 is just canceled away. What if it was, C is 2 by 5 and D is 3 by 5? What would you say about that, about CD? Trick question. CD, what would I say about this matrix? I would say does not exist. Right? It doesn't exist because these 2 dimensions on the inside here don't match up. They don't match up, doesn't exist. In the sense that matrix multiplication is not even possible. So how could I talk about the product C times D when that multiplication is not possible? Okay, here's another example. E times F times G. E is 2 by 3. F is 3 by 5. And G is 5 by 1. No, that's not 1. Let's say it doesn't matter. I'm not going to have us actually do this. And the question is, what is the dimension of EFG? Does it exist? Can we even talk about this product E times F times G? Yes, we can. We can because these are the same. These are the same. What is it going to be? What are the dimensions of EFG? Same thing as before. You can do it multiple times. It's 2 by 4, right? Whatever EFG is, it's going to be a 2 by 4 matrix. Okay, that's a nice trick. was worthy of using this time and this paper to show it to you. Let's do another example of matrix multiplication, if you don't mind. I might ask you guys, what if I have you go in groups? Nah, it doesn't matter, does that? Do you want to be in little groups? Does that help? Do any of your other classes have you get in small groups just to like make sure you know what you're doing? You can talk to each other. Breakout rooms is what they're called. Anybody want breakout rooms, or forget about the breakout rooms? I'm gonna have you do a problem. Do I have it written up here somewhere? Sorry, I clicked the wrong thing again. I'm not getting any feedback either way about the breakout rooms, positive or negative.
Not really.
What'd you say?
I said not really.
Don't want to do it. Okay. You're the only one who answered. So you determined it, that we will not have breakout rooms. Just do this on your own then. Here's the problem. Can you see it now? You should see A in red and B in blue. I don't know what else you're seeing on your screen. Are you only seeing A and B? These two 3x3 matrices?
I see A and B.
Okay. Well, I would like for you to do this if you don't mind. Maybe I'll say the first person to get it right gets a prize.
When you say do it, are we multiplying them?
Oh, sorry, yes. Calculate A times B is the problem. And I won't tell you what the prize is until you've solved it. When you do have it, say, I've got it, and then I'll write down your answer and see if it's correct. And then if somebody else gets a different answer, that'll be whoever gets the answer correct first. Although if you don't want to do this, you don't have to. I mean, of course. If you're, let me say, if you're lost, like what the heck, I don't know what to do. This is 3x3, whereas before they were 2x2. It's the same process where, oh, I can't point. Oh, I can use my mouse here maybe. So for A, you're going to think about the rows of A, 0, 1, and 2. And for B, you're going to think about the columns of B, 0, 1, and 3. So the top left term, I'll just tell you right now, is going to be 0, 1, 2 times 0, 1, 3. And that's term by term. So 0 times 0 plus 1 times 1 plus 2 times 3. It should be 0 plus 1 plus 6. I think it should be 7. It should be the top left term of your matrix. That's probably the easiest one. The rest of them are going to have a lot of. You can use a calculator, maybe. I use a calculator. It's like one of those math contests you'd have in elementary school where you get up on the board and people are like, oh, who can do 9 times 16 fastest? And they just do it. Sorry. Don't think of it as a contest. Just think of it as an exercise. Also, ask me questions if you like don't know what to do. If the 7 didn't make sense, let me know. If now what, after you get the 7, now what do? You don't know, ask me. Whatever time it is. if you were in breakout rooms, you could be doing it together. You could have been like, okay, I'll do this one. Now you guys do this one, and then see which team got it first. But no breakout rooms. $132. Okay. We have 15 minutes. 13 minutes left. Anyone close?
I'm down to the last column.
Okay. Jordan's gonna get it. He's got his sweater. He didn't have it at the beginning of this Zoom meeting, but now he does. It's gonna propel him to victory. Getting a little glare from my window.
I'm done.
It's better. Amina, you have it?
Yeah.
Let's hear it. Give it to me like left to right. First row, then second row, then third row.
Okay, so first row I got 7, 4, 7,
Okay.
and then I got 19, 22, 25,
Okay.
and then 31, 40.
Wait, what? 30 what?
31,
31,
40,
40. And what was the last one?
43.
43. All right, now I'm wondering if did anybody get a different answer than that? I will stop share and oops, I don't have it anymore. Did anybody want to guess something different? Wait a second. I think I can tell if she's right. Oh, I got something different than she did on one of them. Oh. No, I made the mistake. You're right. You're right. It's pretty obvious to see where I made the mistake. Sorry guys, I think Amina got it. Good job. Thank you for telling me this. And excuse me while I fix something real quick. Oh no. Um, 40 for that was the one I missed. Okay. I'm going to share my answer that I wrote out that hopefully will be enlightening. Share. Is it shared? What are you guys seeing right now? Because I'm seeing a lot of my own. Okay. Is that good? So what I hope you guys can see this. It's color coded. I've done a color coding of all the rows and columns that go into these numbers. And my numbers were 7, 4, 7, 19, 22, 25, 31, after I corrected it, 40, and 43, which is exactly what Amina got. So I think we both got the same answers eventually. I think this is right. Did anybody get anything other than this for A times B? Good job, Amina. You win the prize. I'll tell you privately whatever the prize is.
Okay.
But mostly, I want us all to understand how you get all these numbers. I think it's kind of boring to make you do this any more than once. So if you did it this one time, congratulations. That's a lot of crunching math numbers in your head. But you know what? I think it's kind of worth it to have you do it once because you get this practice of row of A, column of B, row of A, column of B, row A, column of B, row A, column B. I actually wrote the rows that they kind of look like a column here. I only did that so that this multiplication would look natural going right across and then adding them together. So just so you can tell what I've done here with these red and blue, that's the first row of A, that's the first column of B. I'm multiplying it I'm cross, and then I'm adding these together. That's how you get this final answer. The big number is the final answer number. 7, 4, 7, 19, 22, 25, 31, 40, 43. Anybody have any questions over how you do this? You may ask, why would I ever care to do this? And that's a fair question. What I mostly care about is that you understand what matrix multiplication is, because that is what will be useful in some higher math problems and higher economic problem, and more advanced economic problems. Not that you actually have to do the multiplication yourself. That's pretty rare that you'd have to do it yourself. And in fact, a calculator, depending on the calculator or the computer, but there's something called MATLAB, which doesn't stand for math, it stands for matrix. And the reason they call themselves MATLAB is because they are very convenient for working with matrices and multiplying matrices or doing anything with matrices. At least that's what I heard. I'm not sure if that's necessarily true, but I believe it refers to matrices, and it's really a way of combining data into one object. Let me just say what I mean here. Imagine the matrix A is actually 9 pieces of data. 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, that's just the numbers between 0 and 8 going in order. But forget that. Imagine this is all like 9 observations of something that you took. It's really nice to take all of those 9 pieces of data and just call them one thing, and that's A. And then later on, we're going to realize that in a lot of ways, you can treat A, the matrix A, as just one thing. You can take A plus B, and that means something. You can take A times B, and that means something. You know what else? You could take B times A. Would that be the same or different as A times B? You guys think? Is AB the same as BA? How much time do I have? 1:39. I have 6 minutes left. Is AB the same as BA? It's a yes or no question. You have a 50% chance of getting right. Jordan's shaking his head. No, he's correct. It matters the order in which you multiply matrices. The word is it's non-commutative. You cannot commute the two A and B and get the same answer. It's a non-commutative operation with the multiplication of matrices. But it actually, once again, if you think of it as data, it sort of means something different. If you take a matrix and the word is pre-multiply it, let's say A is the matrix that we care about. A is the matrix we care about, and B is some operation that we're doing to A. B is some way of changing A in some particular way. It matters if you're pre-multiplying it, that would be B times A, or if you're post-multiplying it, that would be A times B. The effect of this operation of the matrix multiplication changes whether it's pre or post multiplying. Okay, real quick, what else can we do today? Let's do some more definitions of matrix related things. And that is with, like for example, the transpose. The transpose is a very good thing to know what it is. You guys seeing my slides on matrix multiplication? Here's the transpose. Are you guys seeing the slides about transpose right now? Can't tell if
Yeah, I see it.
Oh, okay. The transpose of a matrix is actually a new matrix where the rows and columns are flipped. And actually all matrices have transpose. It's not like something only square matrices have or only certain dimensions. All matrices can be flipped where the first row becomes the first column. The second row becomes the second column. The third row becomes the third column, etc. That's literally all that you do to create a transpose. And sometimes it's written with this A superscript T, capital T for transpose. I have to say sometimes it's just written as a prime. You may think that's confusing because prime refers to derivatives sometimes. Well, I'll try to be consistent and use a capital T, but you might also see it as just as a prime. But that refers to the transpose of a matrix. So if A has dimension m by n, then the transpose will have the dimension n by m. They'd be flipped. That's just what a transpose is. Well, here's another property. If a matrix is equal to its transpose, then it is symmetric. What does that mean? It means if you flipped the rows and the columns, it becomes itself. That's the definition of what it means to be symmetric. You can almost think of a diagonal going from the top left to the bottom right. If you have this diagonal and you just sort of mirror the numbers across that diagonal, that's what it's symmetric with respect to. If it's symmetric with respect to that top left to bottom right diagonal, then you call it a symmetric matrix. What are some other properties? Well, you take the transpose of the transpose, you just get the original matrix. That's always true. If you take A plus B and add them together, like the transpose, it's the same as taking the sum of the two transposes. That's probably pretty obvious. But here's an interesting one. Running out of time. 2 minutes left. If you take two matrices and multiply them, A times B, and then take the transpose, it's exactly equal to if you had taken the product of the two matrices, the transposes of the two matrices, but in the reverse order. What? Yeah, that's true. A times B transpose is equal to B transpose times A transpose. So that's just kind of an interesting fact about transpose. You can always do it, right? This is not one of those things where I might ask you, is it possible to take the transpose of a matrix? The answer is always yes. And let's just say we're out of time. Let me talk about the quiz. It's going to be on Thursday. Do you guys like it better at beginning of class or end? I sort of like end better. But that means I do want to have some of the lecture of the class before the quiz, if we do that. Is that okay? Good. What will I put on it? I will put a question about optimization with one variable. There could be some parameters too, or exogenous variables, and I could ask you about the comparative statics with respect to those, but there's only going to be one choice variable. What do you think about matrices? Can I ask you questions about matrices on this quiz, or should I just stick to the one topic? I'm going to have to ask you about matrices at some point. You feel comfortable if I ask you to do some sort of simple matrix multiplication? How about that? I think you guys could do it. How about that? I'll even tell you that's what's going to be on it. Matrix multiplication. But simple, maybe like 2 by 2. I don't want you to spend all the time that would take you to do a 3 by 3 or 2 by 3 times 3 by 2, something like that.